Welcome everybody to our today's lecture of our expert group of geological mapping and modeling of Eurogeo surveys. My name is Hans-Georg Krenmeier. I'm Vienna-based, and today I have the great pleasure to introduce to you Charlie Kirkwood. He will talk about geological mapping in the age of artificial intelligence. Title is Can Probabilistic Properties First Mapping help us to achieve spatial consistency at pancontinental scales? The background of this lecture is quite simple. Our Secretary General, Julie Hollis, made me aware a few months ago of an article by Charlie Kirkwood, published last year in the journal Geoscientists, with the simple title, Geological Mapping in the Age of Artificial Intelligence. I read this article and found it very, very interesting, easy to understand. And so I decided to contact Charlie, who was immediately ready to give us this online lecture. Sorry, I have to shut the window. Charlie presently is a postdoctoral research fellow at the Institute for Data Science and Artificial Intelligence at the University of Exeter. But he has a background as a geologist and began his career actually in the exploration industries, also field-based work. And moved then in a research position also at the British Geological Survey. So he was more or less a direct colleague of us, where he first published about the topic of machine learning, geoscientific mapping. There is now an echo.
Yeah, I think Tim has his microphone on. Tim, are you able to mute? I think it's coming from you, sorry.
Okay. Thank you. It's better now. So, still the echo there. Okay, Charlie already has shared his screen. Welcome once again to you. If you want to add something on your person, very welcome, and give the stage to you.
Okay, well, thank you very much. And I should start by saying I'm kind of honored to be here, really. To be invited to speak to Eurogeo surveys is terrific. So thank you very much. I do have a copy of the magazine here, which you may or may not have seen. Obviously, well, in large part, this talk is kind of based on the content of the magazine, but there'll be something new in here, even if you've read the article. So don't worry if you have. Okay, so I've already been introduced, so there's not much more I need to say. I'm a geologist by background, but I've just finished doing my PhD in mathematics at the University of Exeter, which was in partnership with the Met Office. And yeah, I'm now working at the University of Exeter. Geological mapping is, I guess, still a topic that's very much of interest to me, kind of quite close to my heart, I suppose. But I've been pursuing the kind of data science methodology that, in my opinion, could be useful for the future of geological mapping. And yeah, I've been introduced already, so you know all this really. I just want to very quickly say a thank you to my PhD supervisors who have invested quite a lot of time in me over the last 4 years or so. And I've learned a huge amount from them, so I thank them very much. So this talk really then is about what AI can do for geological mapping. And given the audience here, then how could this be useful for pan-European mapping and potentially beyond that? But I think that sort of comes out almost self-explanatory when we talk about what AI can do for geological mapping. So you're probably all familiar with the kind of traditional looking geological maps, which this example here is from the British Geological Survey. If you go on the Geology Viewer website, then you can see basically a map that looks like this. And I think it's what we're all kind of used to, which is where geologists have gone out and done field mapping and then drawn polygons, basically delineating different units of rock. And there are some issues with this, I think, which I'm going to talk about. but I'm just sort of highlighting here at the beginning of the talk, when you kind of put them side by side, clearly the kind of AI approach, which is this, and that gives you probabilistic predictions of geological properties at any point, compared to the traditional mapping approach, they look very different, and they're kind of constructed from different principles, but in the end, maybe trying to achieve the same kind of thing. And okay, I don't need to say this because you all know this already. And in fact, I've taken this from the EuroGeosurvey's website. I thought this really resonated with me, that this statement that geological maps are the language of geology. And if we imagine all the fields of the geological sciences as the chapters of a book, then geological maps and models would be the language in which the book is written. So clearly, geological maps are really important. So I think that's why AI for geological mapping is an important topic. So the talk split into 3 parts, and I'll just crack on with the first one, which is a kind of a quick look at history in a way, and where we are today. So if we think about a timeline, this is climate science advances, but it could kind of be a timeline of anything. Just think in terms of general technology, how far everything has come in the last 200 years. I mean, even in the last 100 years, even in the last 10 years, like things are very rapidly developing for humanity, essentially. And if we go back slightly over 200 years now, then that's when William Smith published his first map of the geology of Britain, which, as I understand it, is the first sort of national scale geological map that was ever published. So this sort of set the stage for everything that's come subsequently. And it was only just a very few years later that George Bellas Greenhoff published the second geological map of Britain. And at the time, he was the president of the Geological Society of London, which was just formed in 1807, I think, just a few years before. And because it might be of interest, the British Geological Survey was founded in 1835, so just a short time after that, although it was known at the time, or it was part of the Ordnance Geological Survey. It was the Ordnance Geological Survey. Yeah, so kind of all of our talking about geological mapping seems to date back to this time about 200 years ago. And there's this quote from William Smith from 1839 that sort of outlines his philosophy about geological mapping. And he says that the principles of geology, like those of geometry, must begin at a point through 2 or more of which the geometrician draws a line. And by thus proceeding from point to point and from line to line, he constructs a map. And now we are over 2 centuries later, but I think it's the case for all of our geological surveys that it's still the case that basically our geological maps consist of hand-drawn lines to delineate different units of rock. So this philosophy has just kind of remained continuously for 200 years, really. And I've been referring to this, I do in the article, as classification first mapping, because this sort of act of drawing the lines on the map is really the act of drawing boundaries between different classes of rock. But of course, we know that in the background, there are these kind of formal classification schemes that tell us if we knew the properties of the rock, or if we know the properties of the rock, perhaps in terms of chemical composition or mineralogical composition, or the age of the rock, all these kind of different variables, essentially, if we know what those values are, then we have these classification schemes that will tell us how to classify that rock. So in the background, we do have these formal classification schemes, but I think that the kind of act of field mapping and of the modeling that we do at the moment is predominantly, going out and deciding fairly subjectively what the classes should be, and then drawing our line work to delineate those and to put the boundaries between the different rock types. So you could say, if it's not broken, then do we need to fix it? You could say that, and I think that's largely what we have been saying, I suppose, for the last 200 years. I think we've been quite happy doing what we've been doing. Well, I say that as a geologist, although I'm not primarily a geologist now, I suppose. But anyway, I think the geological surveys have been quite happy to be doing that kind of mapping. But I do think it's the case that this traditional classification first approach has some flaws, basically. And in my mind, the principal flaw in the traditional approach is that these maps are very difficult to compare to reality, because they're not providing, not directly providing measurable properties or predictions of measurable properties. So the map gives us the polygons, say, or the volumes in 3D, and we can look up the sort of information that's attached to those polygons, but it's not a kind of specific point-wise prediction of measurable properties that we could go out with some instrumentation to collect new observations and thereby kind of evaluate the quality of the map. So I think with the traditional approach, it's actually extremely difficult to say when one map is better than another. So I think the reason I've kind of mentioned Smith and Greenoff's map together in the beginning here is that even though they were both essentially published at a very similar time, they are slightly different. And I think it would have been very difficult back then to say which one was better. As it is today, it's really difficult to say which classification first map is better than another. But on top of that issue, these traditional maps also don't quantify uncertainty, which is increasingly a problem, I think, as we try to become more efficient in every way that we interact with the lithosphere, basically. And they often have inconsistencies across map sheet boundaries. You see this a lot for the UK map. If you go on the geology viewer on the British Geological British Geological Survey website, then you can, if you zoom in, you'll see a lot of places where there are inconsistencies. And of course, even if we can be consistent within countries, we still have a problem of inconsistencies when you're talking about trying to be consistent across different countries. So I think for like European scale mapping, yeah, anything we can do that improves the consistency is surely got to be beneficial. And another thing is that basically, because these traditional maps represent the geological system that I think in reality is a continuous system, but we represent it with these discrete classes. And in doing that, essentially information is lost. We lose it to quantization error. You could say, well, we'll just add more and more polygons until we get closer and closer to approximating the kind of true continuous system, but actually that becomes very cumbersome. It's not really scalable. So to kind of illustrate that, if we imagine here that we've got a kind of a transect across part of the map, which is what the red line on the map shows here, if we imagine that that is the same as this x-axis here, so we've just got distance along section line, and then we can imagine that the y-axis here is basically the crosses here might be observations of some geological property that a stakeholder might want to know. For example, it might be shear strength of the rock, and you might be trying to build a tunnel and you'd want to know that. Well, if you look at the traditional classification first map, then you really find that you've just got these polygons, which when you look at them kind of in section, in terms of what they tell you about the properties, they're basically flat. You've just got a series of flat polygons. And these are not telling you anything about basically the distribution of observations of geological properties around those polygons. Like if you assume that they give you the average, say, they don't tell you about the spread of data around the average. So they don't give us data uncertainty or aleatoric uncertainty. And they also aren't providing us with model uncertainty estimates. Like we've got these hard lines on the map, but in reality, those maps probably could be drawn in slightly different places. And ideally, we would want to model that, but in the traditional approach, we're not modeling that. So we're missing out as well on model uncertainty or epistemic uncertainty. So the question is then, is there a better way? And of course, the fact I'm giving this talk means that I believe that there is. Yeah, so I think the better way is actually to step away from classification first mapping and kind of almost go back to basics, really, and then just consider properties first mapping instead. And this would be where, instead of focusing on drawing the lines in between classes, we would focus instead on just mapping the properties that we are interested in. And then afterwards, we can always apply the same classification schemes that we already have, actually, in order to have a classified map. But I think the bigger issue is the one of initially mapping the properties. And if we use kind of AI methods that are available to us today, then we find that we can map these properties basically in a way that is able to quantify the data uncertainty as well as the model uncertainty. So I put a series of points here to kind of emphasize why I think this approach is better. And the first one, and I think it is really the most important, is that properties first maps are directly comparable with reality, because by directly predicting measurable properties, that means we can just go out into the field, collect new observations, and sort of immediately and objectively see how close our map is to reality. And this makes it much easier to assess map quality. So, for example, we can adopt the concept of likelihood which is the probability that the scenario depicted by the map would produce the observations that we see. So that would be a very good way of being able to quickly say, well, is one map better than another? And if the likelihood is higher, then yes, it probably is. So also using the likelihood, and this is quite crucial, it enables uncertainty quantification via Bayes' rule, which we're going to talk about a bit later on in the talk. And that basically is a path towards then having calibrated ensemble geological maps, which at the moment we don't really have those, do we? So at the moment, our geological maps, of our respective countries, I think it's fair to say that they are just sort of single best maps that represent our kind of best estimate of the geology or our best representation of the geology. But there is no ensemble that could kind of represent uncertainty. So we've just got a single best estimate at the moment. And properties first maps have the benefit of basically being consistent regardless of the size of the study area, at least if they're produced using AI methods, because AI has no internal disagreements at map sheet edges. It can ingest huge volumes of data and it can be consistent for kind of any scale of spatial mapping. And it doesn't care about political boundaries or boundaries between different geologists' interpretations. Although I would caveat that by saying it still is important that we incorporate geological knowledge into the system, and I'll talk a bit about that later as well. And also we've got the benefit then of no artificial limits on fidelity, because using the properties first mapping approach, we are modeling the continuous geological system as continuous variables, basically, which is kind of the true form in which it exists. So the interesting thing is that thinking about this properties first approach, even though it may seem almost a bit of a new idea at the moment, although that's not technically true either, because there's geostatistics, which already deals with mapping continuous properties. But as a concept for producing, for example, national or even European scale official geological maps, then I think it is a new idea. But you can still date it back to actually Pierre Simon Laplace, or at least this idea that the most important questions of life are indeed for the most part only problems of probability. I don't think Laplace was really interested in geology, but it's interesting to think that if Laplace and William Smith had got together, given that they were both in a way doing their finest work at the same time, then maybe the history of geological mapping would be quite different. And also here we got Thomas Bayes, because actually, although it's Laplace that said this, then really Bayesian statistics has come from Laplace and Thomas Bayes. So you could say at this point, and you might be thinking it, that aren't I just talking about geostatistics in what I'm saying? And I think the answer is sort of fundamentally yes. But at the same time, the term geostatistics seems to be almost synonymous with ordinary kriging and regression kriging in the geology world. So these are techniques that make quite restrictive assumptions, such as assumptions of stationarity. So assuming that the spatial autocorrelation properties of what you're trying to interpolate are going to be consistent throughout the study area, and then also assuming isotropy, so that spatial autocorrelation would be the same in all directions or all orientations, for example. And those are assumptions that can be overcome. You can add in additional flexibility to geostatistical models, but coming from the kind of geostatistical route of development, it's generally been quite restrictive. But I think that's been partly out of necessity, because our computers, at least in the sort of 60s when these methods were developed, they weren't very powerful. So you had to make quite simplistic assumptions. But then kind of coming from another direction, now we've got kind of techniques emerging from the machine learning or the AI world. And these have grown out of a less restrictive philosophy, basically, with the aim of tackling problems where large numbers of observations are available. And increasingly, that's the case today. Obviously, it was kind of always the case for companies like, I don't know, Facebook or whatever, but now we also have huge amounts of geological data. So the same kind of principles might apply where we want to use machine learning or AI techniques. But the thing is, these techniques are still reliant on statistical principles. So you can't get away from that. And an idea that I have, or an opinion that I have, which is maybe a little bit controversial, but I'm sharing it here anyway, because I think it is important, and I do think it might be why we haven't already moved on to properties first mapping. Anyway, the idea is that I think it's the kind of overly simplistic assumptions of traditional geostatistical approaches that have basically prevented us from moving forward with properties first mapping, because basically, I think as geologists, we look at the output from something like ordinary kriging and we say, oh, well, that actually doesn't really look geologically realistic to me. And I think that's a fair comment, because I think that's kind of true. So here's a kind of illustration of this. So this is I guess a case study, actually a publication I had in 2016, where we're basically mapping or interpolating between cerium concentrations in shallow soils. So we've got point sampled observations on the left, and then here we've used ordinary kriging to interpolate between them, which is Gaussian process regression through space. And then if we look at the mean of the prediction from ordinary kriging, we can see that it looks like a very kind of smooth map, and actually really kind of unrealistically smooth in the mean. So that doesn't really look like geology to me, and I think probably to most geologists that doesn't really look like geology. But then something I was curious about was if we use some machine learning algorithm instead to try and do essentially the same thing, but to predict the concentrations of cerium as a regression on covariates, because we do have all these other data sets available. For example, we do have elevation data, we've got satellite imagery, we've got geophysical data sets, all of which have kind of continuous coverage. So then if we can learn to predict, the concentration of the thing we're interested in as a regression on those covariates, then maybe we can capture a lot more geological structure. And well, indeed, that is the case, basically. So then if you look at the map on the right, it's a bit like putting your spectacles on or something, and suddenly we do get a lot of geological structure. And then that, to me, looks like something that is a geological map. And so this has kind of inspired, I suppose, a lot of what I'm talking about in the rest of this talk, and quite a bit of the work that I've done since. So I think it's the case, though, that really only in the last 10 years, a combination of computing power and more efficient algorithms have made it possible to kind of tackle this in a serious way. I think before 10 years ago, we couldn't really be talking about, trying to do geological mapping in an AI way. We just didn't have the technology, essentially, but it's developing extremely quickly now. So it was 10 years ago, basically in autumn 2012, that kind of deep learning broke into the mainstream. And deep learning, as you may be aware or maybe not, but it means basically using neural networks with many, many layers stacked on top of each other. And they can learn these kind of hierarchical representations of problems in order to make hopefully good predictions. And so the breakthrough was on this competition called ImageNet, which is about classifying images of sort of everyday objects. And prior to 10 years ago, the classification or the classifiers always relied upon basically having manual feature engineering. So people would have to think what kind of filters would be useful to highlight, I don't know, the kettle on the kitchen counter or something like that. And they design a filter that could help to differentiate one object from another. But yeah, so the breakthrough 10 years ago was that actually it was kind of the first demonstration of deep neural networks on a huge task like that of classifying everyday objects. And the deep neural network doesn't require any manual feature engineering. It's able to learn filters for itself that help to distinguish between those objects, or even kind of to do that optimally. And then 10 years later, I got this article in the Geoscientist magazine, and it's on the front cover. And this is a deep learned geological map. Essentially, that's what I wanted it to be. Although it's a geochemical map, but with the level of precision that it kind of becomes a geological map, because it just tells you the geochemistry at each point with a very high level of detail. Anyway, so I think we're at a really exciting time, because we've kind of got this emergence of deep learning, which is a really powerful technology. And people are now working on how we can combine that with Bayesian inference, basically, which is how we do uncertainty quantification. So we're kind of heading towards a future where, well, AI is really becoming more and more powerful. And I think for geological mapping, this means that we're at a point where this question that I've put in bold in the middle of the screen, we can really start to think about that now. And this is kind of the crux of the talk, in a way, or the crux of the point I want to make. So the question is really, can we now, 200 years later, can we now combine the ideas of Smith and Greenough with those of Laplace and Bayes in a way that is satisfying to everyone. So that it means, well, I mean geologists, but I mean geostatisticians as well. I think so far we've kind of had this dichotomy of geological mappers making hand-drawn maps and being satisfied that they can capture geological structure, which is true. And then we've had geostatisticians who are maybe able to quantify uncertainties, but with models that are a little bit unrealistic geologically. And I don't think we've managed to mesh the two together, but I think basically that's where the technology is at now, that we have the possibility of doing that. And I think that's really exciting. Okay, so part 2 of the talk is understanding Bayesian deep learning through the example of mapping. And really, Bayesian deep learning is kind of 2 separate concepts. You can do deep learning and you can be Bayesian. And in this section, we end up kind of combining both of these. But initially, I'm just going to talk about deep learning first, and then we'll move on to the Bayesian inference. So a paper I published in 2022 was called Bayesian Deep Learning for Spatial Interpolation in the Presence of Auxiliary Information. And basically, this tackles what I think is quite a common problem, not just in geology, but in environmental science in general, where we've got, on the one hand, well, on the left here, we've got kind of continuous covariates information about the land that we're interested in. So for example, in this example, we're just talking about terrain elevation data, but it could also include satellite imagery and geophysics and so on. And then alongside that, we've got these kind of point sampled observations of variables or properties that we're particularly interested in. And what we would really like would be to have a continuous map of these point-wise observations. But in reality, we can't just collect a continuous map, because that's sort of prohibitively expensive, for example, or some places are simply inaccessible. So of course we have to make predictions about what's going on in the gaps between our observations, basically. And that essentially is also the same challenge that geological mapping has to tackle. So the method that we published in 2022 is basically a deep learning approach for doing this, or a Bayesian deep learning approach for doing this. And it can produce then maps with a really high level of detail, because they can automatically extract structure from the covariates in the process of interpolating between our point sampled observations. Okay, so we've got this deep neural network here, and this is a kind of schematic of what it looks like. And it is basically inspired by regression kriging. And it combines 2 branches, basically, of data input, or of sort of input information. So this branch here is basically a stack of convolutional layers. And this is what's used in computer vision to recognize objects or features in images, basically. So we can feed in an image of the terrain elevation data centered on each observation, and using these convolutional layers, we can learn to extract sort of meaningful features from the surrounding landscape. And at the same time, we just feed in the usual kind of location information, so easting, northing, and elevation. We feed in the other branch, and this goes initially just through like a single, very wide, fully connected neural network layer. And in the limit of infinite width, that would behave like a Gaussian process, which is what ordinary kriging is. So this is a sort of ordinary kriging-like interpolation branch, where this is a kind of learning from the landscape branch. And these, or the information from both branches, then gets combined in a subsequent 2 more hidden layers, which can then learn the interactions between these things. So the features in the landscape, they don't have to be the same everywhere. They can vary, through space as necessary. And then the neural network basically outputs 2 parameters, mu and sigma squared, which is the mean and standard deviation of a Gaussian distribution. So this means that the neural network will basically give us a Gaussian output for a given input. So if you feed it the information at a particular point in space, it will give us a prediction. And that, in sort of data model terms, looks like this. So, and here I think I forgot to mention, but this is a map of calcium in stream sediment samples across the UK. So at each point in space, we can simulate calcium as a normal distribution, whose parameters are basically functions of global position and local context, a combination of those. So how does this work for mapping? So let's just imagine, going back to this transect example, we've got a transect across a map here. And for example, let's pretend that we want to map calcium concentration as our property, our y, our target variable to predict from X. and X gives us a distance along the line. And in reality, there is some true value of Y through space. So like there is a true calcium concentration that exists. But unfortunately, we don't know what it is. So the best thing we've got is just a finite number of observations, which are inevitably going to be collected with some measurement error. So they give us a kind of snapshot in different locations of what the truth is, but then obviously with a bit of noise, a bit of measurement error as well. So that's what we've got to go on. We've just got these observations that we want to be able to interpolate between in a good way. And going back to this neural network architecture, well, basically the neural network takes as its input what we could consider to be X, and it gives us as an output, as a probabilistic prediction, what we can consider to be Y. And everywhere across the map provides a different input, a different X, basically, because it's a unique location with, it's a unique position in space with unique covariates associated with it. So basically different configurations of the neural network weights, and I haven't really spoken about this, but basically the neural network, it's got that sort of multi-layered representation, but each layer there has got actually, well, in this case, it'd be thousands of different parameters, which dictate the function that the layer provides. So within the neural network in total, there's something like 1 million parameters in this case, and basically the values of those parameters dictate the function that links Y to X. So for a given X, you'll get Y, but the function that tells you what Y will be, is dictated by these parameters. So we can imagine that we could just set the parameters to some random values, and immediately that would give us a function that will predict Y from X. So that's what I've done here, basically. Let's just, well, this is literally a random set of parameter values, and it gives us something that we could consider to be a prediction of calcium concentration. And from it, we can simulate basically pseudo observations. So we can generate new observations from the model already. And if you do that everywhere across the map, then you essentially generate a map. And you could say at this point, it's a map of calcium, but that's a bit of a stretch because at the moment it really doesn't match up with the observations very well. So the question really is, what's the probability that the observations we see in reality could have been generated by this map or model that's defined by the weights W, and that is the likelihood, the probability of Y given W. So in this case, the likelihood is very low, but we can actually use optimization, which is very efficient, running on modern GPUs. And this is really, the deep learning revolution has been powered by efficient optimization, basically. So we can run optimization very efficiently to maximize the likelihood. Basically, if that's what we want, then we can just run optimization to maximize the likelihood. So that would give us a single map then that would be, well, basically would correspond to our observations quite closely or very closely. So we might think on the surface that that would be a good thing and that might be enough in itself. But in fact, it's quite brittle because maximizing the likelihood on training data is not necessarily indicative of good predictive performance at as yet unobserved locations, which is what actually matters, because in the end, you don't really want to predict what you've already seen. You want to predict what you haven't seen yet. That's the value of the map. So it's worth reminding us as well, or ourselves, that I think our current maps, although they are not formally maximum likelihood maps, I think it is kind of, it is unofficially the process we take that we do try and create our maps to be essentially maximum likelihood maps, or like the most likely maps. So we do aim for single best maps at the moment. But the problem is when you have only a single best map, even if it matches up with your observations that you've collected already very well, there can still be potentially big discrepancies between the map and reality when you go to new locations. So for that reason, it becomes really quite risky to trust a single best map. And you've really got no way of knowing how good a single best map is because it isn't giving you an indication of its uncertainty. So instead, we should embrace this idea of the primacy of doubt, which basically is saying that, well, where we haven't observed already, we don't know for sure. what the values of those geological properties will be. We just have to accept that we don't know, and we're not going to know until we observe them. So given that we don't know and we're not going to know, then what's the best thing we can do? And really the most sensible thing we can do is actually model a distribution of plausible maps, essentially, that can represent our uncertainty about, the unknowns between our observations. So we can do this using Bayes' rule. So modeling a distribution over plausible maps, it requires learning a distribution over the neural network's weights W given the training data D. So this is P of W given D. This is what we would like to have. It's a posterior distribution of what reasonable weights are in the neural network given the data that we've got. And Bayes' rule tells us that this posterior distribution over the weights is proportional to our prior belief about what the weights should be, which we can just call P of W, which is here, multiplied by the likelihood, which is the probability of the data given the weights. And the P of D here is called the evidence, and this just works as a scaling factor to ensure that the posterior distribution sums or integrates to 1, which it has to do to be valid. I think we don't need to worry too much about the details of this and the implementation of this. It gets extremely complicated. But in principle, the principle here is that basically Bayes' rule and the process of Bayesian inference is a kind of logical way of going from an initial state of ignorance, essentially, where you don't know what constitutes a reasonable map because you haven't seen observations yet. So our P of W, our belief about what the correct weights of the neural network might be, or the correct form of the map might be, is really wide open. We don't know yet. If we haven't seen data yet, we don't know yet what constitutes a reasonable map. But we can go from this state of ignorance in the beginning and actually refine that to a state of knowledge where we then have this posterior distribution, which is the probability of, it's a distribution over weights or a distribution over functions, or in our case, a distribution over maps given the data. So this then gives us a distribution of plausible maps, which basically will match to the data as well as adhering to our prior beliefs. And so that potentially all looks pretty horrible. I'm not sure I've done the best job of explaining it, but in principle, that's what's going on. And one thing that's interesting here as well, or something that we need to make note of, is that actually this is all very subjective. So your prior belief, for example, the prior belief about the functions that might generate the data in this case, they could be very different. You could ask one person, or in our case, ask one geologist, what do you think the map might look like in, I don't know, somewhere they haven't been yet? And they'll have some kind of hypotheses about what it might look like, but they won't know yet because they haven't been there. And another geologist would have very different hypotheses about what the map might look like. Anyway, so you can do Bayesian inference and you can obtain your posterior distribution, but this is all a subjective thing. And so it's important to be able to validate it somewhat objectively against reality. And then, so the ways of doing this are kind of, we can basically go by what people like Andrew Gelman say, and he's written the book on Bayesian data analysis. And he says that a Bayesian is calibrated if his or her probability statements have their asserted coverage in repeated experience. So that's really what we want. That would constitute a useful map if we can say, if the map is predicting that the gold would be at a valuable concentration with a 90% chance, then you'd want it to be the case that 90% of those instances where that is predicted, the gold actually is at a valuable concentration, for example. And that's then a useful thing for real world decision making. So how can we assess the quality of these predictive distributions? And so to do this, we can use something called proper scoring rules. And strictly proper scoring rules guide us towards predictive distributions that match the true distribution of Y, which is basically to say that they encourage us to make predictions that are as precise and accurate as possible, or as sharp as possible, while remaining honest about uncertainty. And so one example of a proper scoring rule that gets used a lot in meteorology, but I'm not so familiar with it being used in geology, is the continuous rank probability score, or the CRPS, which is the mean squared error between the predicted and observed cumulative distribution functions. And basically, if the CRPS is 0, then the two distributions are the same. And that would then be essentially a very good probabilistic prediction. So now going back to our results with that in mind, and the reason I mentioned proper scoring rules is not really because I think people know about them already. I think in geology, we don't really talk about them much, but basically that already exists, kind of coming from weather forecasting, that already exists. So if we transition to AI geological mapping, there's a whole suite of tools that kind of already exist that we can use to validate probabilistic geological maps in a similar way to probabilistic weather forecasts. So we don't have to start from ground zero. Okay, so back to the results of this kind of Bayesian deep learning approach for spatial interpolation or mapping calcium concentrations here. And so I've already spoken about obtaining this posterior distribution using Bayesian inference, which is what we've done here. And then actually that posterior distribution is essentially a distribution over maps. So if I flick through here now, you can see on the right, hopefully, that well, there's essentially infinitely many maps that can be sampled from the posterior distribution that we've learned, and they're all a little bit different. And basically the differences between them represents our uncertainty about what the true distribution of calcium concentration in the UK is, for example. And it's a very interesting thing as well that even though this Bayesian deep learning approach, unlike traditional geostatistics, it doesn't have any kind of or explicit parameterization of the length scale, for example. But even without that, it's been able to learn to produce simulated maps, which is what I'm showing on the right, that actually have spatial autocorrelation properties, which is what's shown here in these variograms, that are really very similar to the spatial autocorrelation properties of the observations themselves. And this is all assessed on held out test data. So the model hasn't seen the observations we're using to validate here. So I think it's a really quite interesting result in a way that a model that isn't set up explicitly to model spatial autocorrelation actually does end up seeming to replicate the spatial autocorrelation properties of the data quite well. So that's one thing that's interesting. And then also, if we look at kind of more typical validation plots for this model, all using held out test data, then we can see that if we treat it as a deterministic model and we just take the mean of the predictive distribution, then that actually provides a good degree of explanation of the concentration of calcium. The R squared here is 0.74, so it's something like representing 3/4 of the variance in that data. And then we can also look at the probabilistic calibration. So for example, a QQ plot here, which shows us the proportion of observations falling below the predicted quantile for each quantile all the way between like 0 and 100. And basically we find that the predictions are really falling on the diagonal here, which is exactly where they should be. So this is a really pretty well calibrated probabilistic model, which is good to see. And then we can kind of zoom in to a little bit more detail as well. So in the red box here, we're just looking at a section of the map, and A here is just the elevation data. So this was the covariate, and actually the only covariate that we gave into this model. And then B is a map of the predictive mean. So if we wanted to just treat it as a deterministic prediction, this would be our essentially best map, the predictive mean. And it's interesting to see just how kind of detailed this is, I think. It's not an overly smooth thing. To me, it looks like a geologically plausible thing. And C here is a map of the standard deviation of the predictive distribution. So that's a map of the total uncertainty. And again, it's really interesting, or quite, exciting even, to see that it's able to basically be really precise about where it's being uncertain. So you can move, a matter of meters and go from being very certain to very uncertain. And to me, again, that's really a geologically important thing, I think, because you might cross, I don't know, into a new unit where you know a lot less, for example. Oh dear, whoops, mistake. Let me just go back. Yeah, and then we've also got this transect again here. So the green line going south to north across the country, and all of the colored points here are just like independent samples from the predictive distribution through space. So you can see that the overall uncertainty, it varies quite a lot as you go along the section line. Some places we're really pretty certain about, other areas we're really pretty uncertain about. And as well as the total uncertainty, which is kind of represented in the points, we can also specifically look at the model uncertainty. And this is basically the spread and the posterior distribution of the mean of the Gaussian that I was talking about earlier. So this gray ribbon is a 95% credible interval on the predicted mean. And this varies through space as well. But I think an interesting thing is that in some areas, like for example, here, the uncertainty is quite high. And a lot of that is actually in the model uncertainty. So basically here we've got uncertainty that is down to ignorance essentially, and collecting new data, it would appear, would definitely help us there, and we'd gain a lot more knowledge. Whereas here in the south, we've got a high level of overall uncertainty, but actually the model uncertainty isn't really that high. So it might well be the case that collecting more data wouldn't really be worth it there. And this is one of the very powerful things about, well, I suppose Bayesian modeling in general, and this kind of AI approach, is that we could actually use it as a way of essentially optimizing collection of new data to kind of maximize the information gained from that collection. So now that I said all that, going back to the Geoscientist magazine front cover, which I don't know, encourage you to read if you haven't read it. You can find it online as well at geoscientist.com, I think. But yeah, the front cover map here then is basically produced by the same kind of process of Bayesian deep learning that I've just been talking about. But the difference is, in this case, we're predicting 3 different element concentrations at once. So we've got potassium in red, iron in green, and calcium in blue. And I think a really interesting thing about this is that by having essentially multiple outputs be learned simultaneously, you can imagine that this could be a whole range of different geological properties that basically get learned and predicted at once. And then the deep neural network is essentially learning a hierarchical representation of the geological system with quantified uncertainties. And to me, that's a really exciting prospect. So again, we can validate this, and I did that in the magazine article. Essentially, for all 3 elements here, we perform really well in terms of deterministic prediction using the mean, but also in terms of probabilistic calibration. So it's a really high quality map, I would say. I mean, obviously I'm biased, but I think that's objectively the case. And I hope that this helps us to pave the way for a probabilistic future for geological mapping. I should also at this point say that I'm not the only person talking about this stuff, and probably some of you in the audience are already doing work in this area. Well, maybe the main name in Europe that springs to mind would be Florian Wellman in Germany, who works in Bayesian modeling as well. So I'm not claiming that I'm like the only person doing this, but this is my perspective on the challenge. And part 3 is extremely quick. It's just a single slide, and it's just the implications of adopting the properties first geological mapping powered by probabilistic AI. And I think there's actually loads of implications, probably more than I've written here. But initially, we would have much more transparency about the accuracy of our maps, and uncertainty would be quantified. And that means hopefully fewer nasty surprises for users of geological maps. It would allow decision makers to be better informed about the risk they're taking on by making any decision using geological information. The model uncertainty, the epistemic uncertainty, can be used to optimize collection of new observations. I already mentioned that. And I truly think that this whole technology could give us better outcomes in the climate crisis. The lithosphere is undoubtedly an extremely important part of the Earth system, or maybe even the most important part. And, you know, it's a source and a store of carbon. And I think our current classification first maps are kind of obscuring potentially the opportunities that we need to be able to see in order to be able to do things like capture carbon, or even just optimize, you know, things like agriculture. All round, we can be a lot more efficient if we've got higher fidelity probabilistic geological maps to work with. It also provides a way to unify previously disparate point sampled observations and analyses into a single model of the geological system. I think a lot of how geology is done at the moment is sort of, I suppose, you know, we take an interest in a certain aspect of something. Maybe we're interested in dating rocks, for example, or, well, who knows what, geochemistry, maybe in fossils. So we go out and we collect these sort of point-wise, maybe rock samples. We take them back to a lab and we run some analysis and we collect some data. But at the moment, there is no system for kind of assimilating all of that data. So our maps don't really keep up with the kind of discovery that's going on at an individual geologist level. And I think AI would provide us a way of doing that, so that all of our individual data collection would contribute directly to improvement of our overall knowledge of the lithosphere. And also, I want to kind of emphasize that this isn't this doesn't mean that kind of individual contributions will be any less valuable. I think it's kind of the opposite. And also, if we transition to kind of probabilistic mapping, it actually opens the door to using things like model averaging, which would mean that different individuals or different groups who may have different prior beliefs and therefore come up with different, basically posterior maps or posterior ensembles of maps. We can use things like Bayesian model averaging to combine those. And I think that's a much cleaner way of combining the opinions essentially of different geologists, rather than have different geologists map different areas of a country and then really struggle to mesh those together, which leads to the map tile boundaries that we still have issues with in the UK. And I think all of this would no doubt lead to new geological discoveries, because the quality of information we'd obtain would just be, well, I would say very much better than what we have at the moment. And yeah, we would have no more mismatches across map tile boundaries. And if we're talking across different countries, which today we are talking about that, then I think this would be extremely useful, because we get to learn consistent information regardless of which country we're in. So it should make mapping all across Europe relatively much easier, I think. So on that note, thank you very much for listening, and congratulations if you are still listening. I apologize if I've overrun, which I think I have. Sorry about that.
You have, but it was very inspiring and very interesting, good information. Thank you, Charlie. And before I ask for questions, please